Good day, I'm Norman Walberger. In this video, I want to introduce you to the threefold symmetry of what I call chromogeometry, which is a remarkable 21st century development in modern geometry. And it's basically an observation about the fact that we can view planar geometry in three coherent but different ways, where Euclidean geometry is only one of the three possible ways, and the other two are complementary kinds of relativistic geometries. In the context of the projective line, that means that there's not only the blue Euclidean geometry that's available, and also the red relativistic geometry that I talked to you about last time. There's also this third geometry, which is called green geometry, which I want to talk about today. So there's a remarkable symmetry between these three different kinds of geometry, blue, red, and green, and it's visible already in this one-dimensional setting. So this unites Euclidean geometry and two relativistic geometries, but it does also something else. It transcends Felix Klein's Erlangen program. This is a very important direction for geometry, almost a definition of what geometry was, introduced by Felix Klein in the 1800s, and really had a major impact on the way 20th century mathematics thought about geometry and its role. So we're going to go beyond that. We're going to see that in fact the Erlangen program ultimately is too limiting and that we need a broader vista. And there will be many new possible theorems that are created from this view, just having to do also with elementary planar geometry. So lots of opportunities for amateurs or professional mathematicians to get involved and start discovering really interesting and ultimately kind of fundamental facts about the real world, which have been up till now sort of hidden to us. It's really quite a remarkable thing. So let's have a look at this green relativistic structure, a third kind of projective quadrants that we can impose on our projective line. So we're going to define a new quadrants defined by q of x1, y1 to x2, y2 is this quantity here. It has the same numerator that we're familiar with, x1, y2 minus x2, y1 squared. There's a minus sign out front, and in the denominator it's just the product of all four entries, 4x1, y1, x2, y2. This is also conveniently homogeneous. If we multiply the first proportion by 5, then the numerator gets multiplied by 25 and the denominator also gets multiplied by 25, so it stays unchanged. And it turns out that this same expression can be rewritten as 1 minus x1 y2 plus x2 y1 squared over 4x1 y1 times x2 y2. Call this the green projective quadrants. The equality here rests on the following identity. So here's another kind of identity in the same direction as the Fibonacci identity, but somewhat different. x1 y2 plus x2 y1 squared minus x1 y2 minus x2 y1 squared equals 4x1 y1 x2 y2. And it's almost obvious, if you square this, then the squares of the outside two things will cancel with the squares of the outside two things here. And then what you get left is the cross terms here, which is 2 times the product of all four, and then plus 2 times that same product to give 4. Let me say a little bit about the physical significance. So this will be familiar in some form or another to physicists who are watching this. So what we're doing here is really looking at the relativistic plane projectively, but we're sort of changing coordinates, if you like, so that the usual null points, ones I called a plus and a minus, are rotated so that they form our basis vectors. So this is a very popular thing to do in physics, and so it's well known, and so physicists will perhaps see that this is quite familiar. And they might actually wonder why we're doing this, and they might say, well, this is just the red relativistic geometry rotated around, so what's the point? Well, the point is that it's this threefold symmetry that arises, which is not at all obvious But you will see that once we introduce this thing, it really does have a place beside the red relativistic geometry. It's sort of an equal partner in some ways. Okay, so along the same lines as we talked about with the red relativistic geometry, we can define null lines. These are lines for which the kind of quadrants we've defined here doesn't make sense because the denominators have a 0. So if we have a point 1 to 0 or 0 to 1, those points will contribute a 0 in the denominator if we've tried to form a quadrant with them. So they have some special role. They're called null lines. We also have an underlying notion of perpendicularity, which is that x1 to y1 is perpendicular to x2 to y2 precisely when x1 y2 plus x2 y1 equals 0. This is the bilinear form that's really underneath this geometry, and it's appearing here and in fact also here. So the perpendicularity, here's an example, 3 to 1 is perpendicular to 3 to minus 1. If you multiply either of the coordinates by a minus 1, then you get a perpendicular projective 1 point. So let's look at some examples. Our familiar projective line, 3 to 1, 1 to 2, 1 to minus 1, 2 to minus 3. Let's compute some projective quadrants in this green fashion. So for example, between 3 to 1 and 1 to 2, we'll use this formula here, that the quadrants is 1 minus the dot product between these, the green dot product, which is 3 times 2 plus 1 times 1, all squared, divided by 4 times the product of all four things, 3 times 1 times 1 times 2. And that turns out to be minus 25 over 24. So that's the green quadrants between these two 1 points. Between 1 to 2 and 2 to minus 3, similarly we get 1 minus 1 times minus 3 plus 2 times 2, all squared, divided by 4 times the product of all four things. You can check that that's 49 over 48. And between 3 to 1 and 2 to minus 3, you can check that we get 121 over 72. And your first exercise is to show that, in fact, these three numbers also satisfy the projective triple quad formula, which we can write efficiently as S of the three quantities is 0. So I remind you that S is A plus B plus C all squared minus 2 times A squared plus B squared plus C squared minus 4ABC. All right, so that's a very nice story. Note that I've put the axes in green here. The axes are actually the null directions in this geometry. Those are the particular 1 points that you can't create quadrants with other points because there will be a 0 in the denominator. So they play the same role as did the red lines that we talked about in our red geometry. Okay, so here are some familiar exercises for you. First of all, show that the green projective quadrant satisfies the same kind of range of values as does the red one. Namely that it's always less than or equal to 0 or greater than or equal to 1. Never gets in that range between 0 and 1. That's reserved for the blue Euclidean projective quadrants. And show that the familiar projective triple quad formula also applies to this relativistic situation. All right, so now we get to chromogeometry. What is it? Well, it refers to a threefold symmetry between the blue Euclidean geometry and the red and green relativistic geometries. These three geometries connect with each other. There's a symmetry between them. So this symmetry has two aspects, sort of an elementary and a more sophisticated one. At the elementary level, the claim is that there's an essential unity between all three. That if we look at things in the right way, we can expect the same kinds of phenomena to appear in the blue, red, and green. Now this is not universal, this is just a general tendency. Okay, this is what expectation that we have. Sometimes it's not exactly the case, but more or less we can expect that mathematically these three geometries are actually much more similar than they are different. And then the more sophisticated and ultimately more interesting aspect of chromogeometry is that when we consider all three geometries at once, remarkable new relations come into view. So it's the interaction between these three geometries that's somehow really special and unique and seemingly doesn't have an analog in other areas of mathematics. Of course, in physics, physicists are very interested in threefold symmetry because fundamental particles have a kind of chromo aspect as well. Physicists talk about red, blue, and green in their chromodynamics theory. It's sort of interesting to speculate whether this might have anything to do with that physics, but that's purely speculation. All right, so let's have a look. So what actually goes on here with this new subject of chromogeometry? So I hope this background rain is not too distracting. It's been bucketing down in Sydney for the last few days. Okay, so we are going to introduce some notation now so that we can deal with all of these three geometries at the same time and to distinguish them. So let's introduce superscripts B, R, and G to refer to blue, red, and green. So we'll now talk about the blue projective quadrants, the red projective quadrants, the green projective quadrants, and here are the various formulas for them. I'm going to put the 1 minus formula first. There's a little bit more uniformity between these different expressions. We're basically just replacing the bilinear form with different kinds in each situation. And here are the alternate forms, the more original ones that always have the same numerator term, x1, y2 minus x2, y1. So there's corresponding bilinear forms here, if that means anything to you. I'll just write down the matrices for the blue, red, and green bilinear forms. So these are sort of the matrices that create the bilinear forms that are occurring here in these three different expressions. We will be talking more about what bilinear forms are and so on at greater length later on. I'll just put that there for reference. Okay, so these are our three basic ways of measuring, and we're going to be thinking about having our pizza with all three geometries going at the same time. So there's three different projective quadrants all happening at the same time. Okay, so our first theorem in chromogeometry is the colored quadrants theorem, which asserts that for any projective 1 points A1 and A2, the three different quadrants, the blue, the red, and the green one, are related. There's a relationship between them. And it is 1 over QB of A1, A2 plus 1 over QR of A1, A2 plus 1 over QG of A1, A2 equals 2. The proof? Well, it follows from this identity right here. This is an identity. x1 squared plus y1 squared times x2 squared plus y2 squared minus x1 squared minus y1 squared times x2 squared minus y2 squared minus 4x1 y1 x2 y2 equals 2 times x1 y2 minus x2 y1 all squared. So if you just take this expression, divide by the square here, so there's just a 2 on the right hand side, then you can see that each one of these things is the reciprocal of the corresponding quadrants. So for example, if we look at our favorite two projective 1 points, namely 1 to 2 and 3 to 1, then we've seen that the blue quadrants between them is a half. The red quadrants between them is 25 over 24, and the green one happened to be minus 25 over 24, which you might have thought was a coincidence then. And now we see that the relationship between these three numbers is 2 plus 24 over 25 plus minus 24 over 25. In other words, the sum of the reciprocals of these things does in fact equal 2. And we can see sort of why these are negatives of each other. It's because this one's a half. If this one's a half, then its reciprocal is 2, which will exactly cancel out with a 2 on the right-hand side. And then necessarily, these two have to be negatives of each other. So it's actually a rather general situation that happens whenever we have 45 degrees in the Euclidean setting. Of course, 45 degrees is rather arbitrary, isn't it? I mean, it's going back to the Babylonians. Much more sensible to talk about a projective quadrant of 1/2. That's the real number that's associated to lines that are like this. Okay, so very attractive fundamental relation that shows that, yes, indeed, there certainly is some kind of thing going on between these three different types of geometry. They are interacting. Whenever we have a notion of projective quadrants around, we have an associated notion of perpendicularity. So in the blue setting, that's perpendicular. But in the red and green geometries, perpendicularity has a different meaning and a different physical manifestation. So we want to consider them all at once, so we need some way of referring to each one. So we'll introduce these subscripts, B, R, and G, besides or just behind the usual perpendicular sign. So if A1 and A2 are two projective points given as usual, then we'll say that A1 is blue perpendicular to A2 precisely when x1, x2 plus y1, y2 equals 0. They're red perpendicular precisely when x1, x2 minus y1, y2 equals 0. And they are green perpendicular precisely when x1, y2 plus x2, y1 equals 0. So we have three notions of perpendicularity. And closely associated to that, let's talk about what we might call perpendiculars. So given a projective 1 point, there's exactly one line which is perpendicular to it in any one of the given geometries. We can call that the perpendicular line. So if A is equal to x to y, then let's define A super B to be minus yx, A super R to be y to x, and A super G to be x to minus y. We call these respectively the blue, red, and green perpendiculars of A, because these two are in fact blue perpendicular, because this times this plus this times this equals 0. These two are red perpendicular because this times this minus this times this equals 0. And these are green perpendicular because this times this plus this times this equals 0. Sort of canonical perpendiculars for any projective 1 point. All right, so for an example, if A is our projective 1 point 1 to 2, then its blue perpendicular is minus 2 to 1, which is here. And that is the usual blue perpendicular, the standard Euclidean one, denoted by the familiar blue square there. Then A sub R, the red perpendicular of this, will be this one here, which is to us just the reflection of this line in the line y equals x, or the line y equals minus x. So regular Euclidean or blue reflection. The green perpendicular of this one is 1 to minus 2, which is this line here. The green perpendicularity is expressed like that little angle there in green. And again, this is the reflection in the green null line in a Euclidean sense. So green perpendicularity just amounts to reflection in either of the coordinate axes. Red perpendicularity amounts to reflections in the lines y equals x or y equals minus x. And the blue perpendicularity is the usual one, rotation of a quarter turn. Okay, now we have this theorem that for any projective 1 point A, there is a relationship between these three perpendiculars. A super B, A super R, A super G have a relationship. And the relationship is that the blue quadrants between A super R and A super G is equal to 1, which is to say that they're perpendicular in the blue setting. Let's see what that means. So where's A sub R? Here's A sub R. Where's A sub G? Here's A sub G. The claim is that this one and this one are in fact blue perpendicular. I think you can see that they are. The next statement says the same thing, that the red quadrants between A super B and A super G is also 1. That means these two things are red perpendicular. So A super B is there, A super G is there, and yes, these are red perpendicular. Geometrically, they're reflections of each other around this line y equals minus x, or y equals x. And finally, quadrants green of A super B and A super R is also equal to 1, so there's another perpendicularity there between A super B and A super R. These are green perpendicular. One's the reflection of the other in either of the coordinate axes. And the proof, well, it's a relatively simple computation. If A is the point x to y, then this first thing is the blue quadrants between y to x, that's A super R, and x to minus y, which is A super G. And when we take the blue quadrants, you can calculate that that's equal to 1. Because it's 1 minus something with the dot product in the numerator, the dot product here will be 0, so it'll just be 1. Similarly to the next one, we're taking a red quadrant between A super B and A super G. So again, it's 1 minus something with a dot product in the numerator, and the dot product is this times this minus this times this, which is 0. So we get 1. And the green quadrants between A super B and A super R, there's A super B, there's A super R. The green quadrants is 1 minus something with a dot product, which is this times this plus this times this, which is 0. So again, we get 1. So there's actually quite a lot of different perpendicularities floating around in this diagram. Not just the original ones, but also new perpendicularities between the perpendiculars themselves. But these three colors are interacting here. You see that you need all three of them to really see what's going on. Okay, so reference for this is my paper One-Dimensional Metrical Geometry, which I've also mentioned a few videos ago, in Geometriae Dedicata 2007, if you want to have a look. So I'd like to next time explore this world of these three different geometries, still in the one-dimensional setting. But I want to connect it a little bit more with some geometry and some physics. So I want to talk about connections with Einstein's special theory of relativity very briefly. And I also want to give you a physical way of thinking about what the meaning of these projective quadrants is. Okay, we have a reasonable understanding of what the Euclidean one is, but what do the green and the red ones mean? Well, it'll turn out that we can understand that through the use of a lovely tool, which I'm going to call Paul Miller's protractor, named after a viewer at this channel who made some interesting discoveries. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.